This is Algebra 2 with Trig, working on Unit 4.1, the relationships between functions and their inverses. Our plan for today is I can create a table and a graph of an inverse of a function given a table and a graph, typically of an original, and then you can figure that out of an inverse. I can determine whether the two functions are inverses by analyzing the table and the graph. That's kind of what we're looking at here. We're looking at the table, and we have a particular graph, and if you notice the inverse, all the x values become the y values, and all the y values become the x values. -2, -1, 0, 1, 2, -2, -1, 0, 1, 2. So the x values become the y values become the x. And in that case, what happens is the original graph gets reflected over the line y equals x. And that's a pattern that we're going to see for each one of these. I have a Desmos example that you can copy and paste, and you can see the different points in it laid out. Okay, so what do we notice here? The x and y coordinates have been switched. So for an inverse relation interchanges the x and y values of the original relation. So you have your original graph. When you reflect that over the line y equals x, some people say reflect it in the line, whichever. When you reflect it in the line, you produce a new graph. So let's see what it is here with these tables. We're going to take our original table. We're going to make an inverse table. So we're going to take all our x values and make them the y values. We're going to take all the y values and make them the x values. And that's going to actually reflect it over the line y equals x. So if we were given an original graph at -3, 2, -1, 12, 0, 47, 2, -8, 7, -32, seems a little crazy. Perhaps that's some sort of parabola. Absolute value maybe. If we reflect that over this line, so those points are going to come straight across and reflect across it. This one will go that way. Let's see if we can approximate where this would be. We'd be 2, -3, would be 12, -1, would be 47, 0, we'd be -8, 2, and we'd be -32, 7. So my units aren't very uniform here, but I believe these are the points that are matching up. So they're just being reflected across this line y equals x by switching the x values to the y and the y values to the x. Here's our original table. We're going to put all the y values as the x values and all the x values as the y values, and now we've made the inverse table. So you plot these points and you can connect them to have your graph. So if you have the original table, or you can make a table, you can easily create a table for the inverse. Now if the x's and y's are interchanging, then that means the domain and the range are interchanging. If the original graph is from 0 to infinity, what that might look like are your x values are going to be from 2 out to infinity. You're going to have x values that are that direction. You're going to have y values that are from negative infinity all the way up to wherever 5 might be considered. So what that's going to mean is this would be a solid dot. We have to go down towards negative infinity. It would look something kind of like that. We don't know the slope, we don't know all those little details. This is just the domain and the range. Well, if we were to do the inverse, if we were to reflect this over the line y equals x, then your range is going to become your domain. And your domain is going to become your range. Because all your x values turned into y values, which is your range, and all your y values turned into x values, which is your domain. Alright, here we're dealing with pi over 2. We haven't really talked about doing pi over 2 and what that might mean. That's going to come up in the unit circle in the future. But for the inverse, your domain is your range. And your range is your domain. Pretty simple. Your y values turn into your x values, and your x values turn into your y values. On the flip side, we're looking more at how the graph itself is working. We have the line 3x minus 1. So we're down at negative 1, and we have a slope of up 3 over 1, up 3 over 1, down 3 backwards 1, down 3 backwards 1. So we have our equation. We have the line y equals x, and that's our reflection line. So if we're going to graph the inverse, there's a couple different ways we can do this. An easy way, what we're going to call this is f prime of x. Which is essentially just your y value. It's your new y value, the inverse, so it's prime. We're going to switch these so they go in the opposite order. And we can plot those out. So negative 7, negative 2, negative 4, negative 1, negative 1, 0, 2, 1, and 5, 2. This is your new line. This is your f prime of x because it's your inverse. And actually at this point we haven't talked about writing the equation, so we won't worry about writing the equation, but this is your f prime of x. This is your inverse. Here we have our x, f prime of x. Making a table. So we switch our x and the y. We graph those out. Look what's going to happen. Here we have a parabola. Now we're going to reflect that. That means we're going to take this and we're going to fold it. Fold it along that line. So what used to point upwards is now going to point sideways. We're going to see that happen right here. So 0, -2, -3, -1, -4, 0, -3, 1, and 0, 2. So that is your f inverse function. So it used to point up for the y's. When you reflect it over the line y equals x, when you fold it, take that paper and fold it over the line y equals x, it's going to produce this graph on the side. Alright, the dotted line on the graph above is our y equals x. What do we notice about the graphs of the inverse and the original in regards to that? They are reflections of each other. They're reflecting over the line y equals x. The graph of a function's inverse is the reflection of the original function on the line y equals x, or over the line y equals x. That's how you can get your graph. Yes, you can make a table and you can plot them out. You can also consider the points and reflect them across the line y equals x. So let's give that a try. So we're going to start up at 6. We're going to do our slope of up 2 over 3. Now we've run out of room, so now we're going to go down 2, backwards 3. 2 negatives make a positive, so it still has a positive slope. So that's your equation, y equals 2/3 x plus 6. We have our line of reflection on y equals x. So it just follows the diagonals straight across. Now we could look at the table, or we could do the reflection. So you go diagonal 1 step, diagonal 2 steps, and a half, 1 and 2, and we reflected it just like you did in geometry class when we reflected values over lines. 1, 2, 3, half diagonals. There's a half. 1, 2, 3. 1, 2, 3. Missed that one. 1, 2, 3, 4. 1, 2, 3, 4. So it took 4 to get to the line of reflection. So now we're going to go 4 to get past the line of reflection. So that's a quick, easy way to create the inverse by reflecting it over the line y equals x. Our last one, this is a parabola. Down here at -8. Now a parent function is going to be over 1 up 1, but this has an a value of 2, so we're going to multiply that by 2, and that means we're going to go up twice as far. Typically you'd go over 2 and go up 4, but now we're going to have to go up twice that amount. And then we usually go over 3 up 9. So that's 8, 9, but we got to go up twice that amount. So we're going to go up 9 more. So there is your parabola. Alright, so we have our line. Y equals x. We should write our equation for our parabola. We know that one. So we could either count or we could make the table. If we make the table, we know that we have a point at 0, -8. We have a point at 1, -6. We have one at -1, -6. We have 2, 0. We have -2, 0. So our new graph, our f prime of x, is going to be the switch of those. 0, -2. -6, -1. -8, 0. -6, 1. 0, 2. So that's a different way to create the graph of your inverse. You can do it through the tables, or you can do it by reflecting it and counting the diagonals to get to your y equals x. Y equals x has a slope of 1. When you come across, you have to be perpendicular to that, so that's why we go at the diagonals, which is a slope of -1.